Hi, my name is Jonas. I'm a PhD researcher in the ML4Q project, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum project answer questions about their work in the project, their research, and the future of quantum. In today's episode, I'm talking to Martino Calzavara. He is a PhD researcher in the ML4Q project, studying thermal cycles in ultracold Bose-Einstein condensates from a theoretical point of view, and also looking forward to use neural nets and artificial intelligence in order to do so. We will also talk about the fattest Schrödinger cat ever made and him moving to Germany and settling down here. So welcome, Martino.
Thank you.
So before we talk about the work that you are doing now in the ML4Q project, let's talk a little bit about your past. So originally you studied in Italy in the city of Padua, which is in the northern part of Italy, and you investigated dark solitons and also graphene from a theoretical point of view. So maybe let's talk a little bit about that. What are these topics actually and what did you do?
So for my bachelor thesis, I worked on solitons in the Gross-Pitayevsky equation, which is a model, a very simple model that you can use to describe a system of cold atoms, which are, by the way, also the kind of system on which I'm working right now. And so in practice I investigated this kind of solitons, which are solution to this Gross-Pitayevsky equation, which are traveling waves. Actually, they can be found also in other systems which are perhaps less exotic than gas or cold atoms. Solitons can be also found in shallow waters, stuff like that. Then I also worked on graphene for my master degree. That was harder, I have to say, because you start to play with some more complicated models. But it's also interesting.
While finishing his master's, Martino had not made a decision yet whether to do a PhD or not. So let's find out how he actually decided to make a PhD and how he found out about the Quantum Control Institute in the ML4Q project in Germany.
Just after my master degree, I wasn't really sure about what to do. And that was a problem that I carried from just after my bachelor, because in the end I didn't start to study physics because I had a very clear idea in my mind of what I would have done as a job later on in my life. I did that more out of curiosity, let's say, and as a challenge also to see if I could do that. So that could be good, but that has also the counter effect that at some point you have to decide what to do. So right after my master degree, I reflected for a long time, and I decided that perhaps I wanted to do something more applied, we could say, with respect to the things that I was working with during my master thesis, which was, by the way, this study of these theoretical models of how interactions works in graphene. So I started to look around a little bit and, looking for something that could bring together some interesting aspects of physics. The true reason why I started physics was, of course, to learn and understand quantum physics. So finding a job in which I could apply that kind of knowledge would have been wonderful. So I started to look into that direction. And it was pretty fortunate that around that time, so in November of 2019, Professor Calarco came to give a talk in Padova. The stuff he was talking about, which is quantum control, really looked like the right thing for me. So since Professor Calarco has been at least a close collaborator of another professor, which now works in Padova, which is Professor Montangero, through him I asked him if there was any open position in Professor Calarco group, and then I applied for this position, came here, did the interview, and now here I am.
Yeah, that's good to have you. So that's actually quite interesting. So Professor Calzavara was coming to that university in Italy and giving a talk. So what was he talking about? What were the topics that he was covering? Do you still remember?
Yeah, I do remember. The title of the article was something like the fattest Schrödinger cat ever made, which more in practice is, the problem of controlling a system made out of many atoms. So in that case, many means 20, I think. The task was to drive the system from a certain ground state to another one. But of course you don't want to do it slowly, which will be the most easy way to do that, because after all, if you move slowly enough, you can start from any ground state and end up by tuning correctly the parameters of the model, you can end up in another state that you want. But the problem is that takes a lot of time, and all quantum optimal control is about is speeding up that process, So instead of performing this adiabatic transformation, the idea is to look for some smart way of doing that fast. So, and Professor Calzavara usually explains that by showing how a waiter can bring around a tray full of wine glasses, without spilling any of it, and not being fired for being too slow to serve the client. So it's something that everyone can relate to in some sense.
That's true. Okay, and then you were, I guess, quite impressed by this talk, and that's how you basically came. Did you know at that point in time that his institute was in Germany, or did he tell that?
Yes, I did.
Okay,
I did know. Yeah.
So you basically knew at the point where you applied that you would have to go abroad to basically join his work group. Yep. I mean, that's quite a big decision to make, right? So
it is. I mean, it didn't look that big back at the time, but now that I've been living here for 6 months, I realized that that has been a very big step in my life, perhaps the biggest one that I took up to now.
So what was your first impression when you came to Jülich? So you told that you were invited for this interview, and then you came here. What was your first impression?
I found it very impressive because, the entrance is quite this large road with the signs and everything. I mean, I was impressed, I have to say. And I had this nice interview to talk with all the people in the group, which back then it was February 2020, so we didn't have all the kind of complications that we have today because of Corona. So everyone was at the office working, so I had the chance to talk with everyone in person. That was nice. I had a very good impression of this group, which back then counted very few PhDs, because I think they were 3 back at the time. But now we are much more than that, because we have been expanding a lot.
Yeah, which is probably also part of the ML4Q project, right?
Yeah.
Okay, so just to phrase it once correctly, so now you're working in the Institute for Quantum Control led by Professor Calzavara, which is working on techniques from quantum optimal control with applications in few and many body systems for the development of quantum technologies, which is quantum computing, quantum communication, quantum simulation, and also quantum sensing. That's what I took from the website. How is it actually probably different also from the work that you were doing in Italy? Like, how's the work life probably different? Of course, there are differences now because of the pandemic, but probably also in other regards, work is a little bit different.
There are also many differences because, back in Padova I was a student, and here instead I'm a PhD student, which is kind of different. So I don't know how it works in Germany, but usually, like, if you're a master student working on your thesis, you don't have an office in Italy, so it was pretty nice to have one here. And now, the big difference is more on the side of the personal life, I would say, because back in Italy, I lived with my parents still, also during the years of university, because so Padova is my hometown, and I grew up there. So and I also went to the university there. So it didn't really made much sense to me to move away. And so the big difference is now that I have to care about everything on my own.
Yeah, that's
so that's the big thing, because that takes away a lot of time and energies, and to start to put that together with the new responsibility due to the job itself. That's challenging. That's a big difference.
Yeah, that's true. I also remember when I was in Italy, most of the people that I got to know actually lived at their parents' house. I think it's quite normal because you have big families, and then usually the families also way more together than probably here. Something else that I also realized back then was most of my colleagues, they were actually basically taking bringing something to the institute to eat from home. So they didn't go to the canteen at the university. I don't know how it is in Padua, but
it depends, because there are several good canteens in Padua. You have to walk a little bit to get there. So there is always that option. Personally, I always ate at the canteen when I had to stay at the university in the afternoon and stuff like that. Otherwise, I would just go back home and have lunch with them.
Here in Jülich, we have the See Casino, which is the canteen of the research center. How is it here? How do you like it?
Not bad. Yeah.
Perfect. This is actually quite positive feedback from an Italian for the See Casino.
Also the pizza is not terrible, I have to say. I eat it sometimes.
So thumbs up to the canteen here in Jülich.
Not the pineapple one.
Yeah, that's strange.
Not
right?
the pineapple one. Okay.
But okay, that was a little bit about the campus life. So maybe let's talk also a bit about the work that you are in right now. So what are you doing now?
Let's say first of all that we are a theory group, okay? But we work a lot in collaboration with some group of experimentalists, especially in Europe. What we're trying to do in collaboration with this group of experimentalists is to build let's call it a quantum refrigerator. The platform on which we're working is called Atoms, as I was telling you before, which means that basically you take this gas of alkali atoms and you cool it down at a very, very, very low temperature. So we're talking about some 100 of nanokelvins.
So that's even way colder than the universe, right?
Yeah.
It's probably one of the coldest spots in the whole universe.
Yeah, indeed. Back in the 90s, I think that this kind of systems reached the record for low temperature. But I don't know if that still holds to nowadays, but it's still pretty cold, pretty close to the minimum temperature that you could achieve at all. So what happens to these kind of systems when you cool them down? They condense. So these atoms, in our case, are bosons, which means that so all particles are either fermions or bosons, and that tells us something about how do they behave when they are put together in a system, So bosons usually want, let's say, to stay closer one to another, and they like each other. So when you cool them down enough, they condense, and they form a so-called Bose-Einstein condensate. And you can do a lot of stuff with this kind of systems. So in these years, the experimentalists in general have been very successful in implementing some very refined control techniques on this kind of system. So you can even tune the interaction interaction strength with which these atoms interact. So you can really explore a wide range of physical parameters which characterize these kind of systems. So, as I said, a quantum refrigerator, what does it mean? So it means that we would like to take one of these Bose-Einstein condensates made out of cold atoms and implement, let's say, a thermal cycle, just like the one that make the refrigerator in our houses work. So basically the idea is to use the compression and the expansion of a part of the system to drive the heat from a cold reservoir to a hot reservoir, and this way, cooling down the cold reservoir. In order to do that, as thermodynamics teaches us, we have to do work, and this work is performed on this kind of systems by shining lasers on top of these clouds of atoms, and so this laser can, in practice, move around these atoms. They project an external potential, how we say it on this system, and this potential can take the shape of a well, the size of which can be compressed or decompressed, so that we can, at least in principle, achieve this kind of thermal cycle.
How big is this well?
Some 100 micrometers.
Okay, so a very, very small
yeah.
spot, but probably also very few atoms, right?
It's about 10 to the 3, 10 to the 4 atoms, something like that. Yeah, not a lot, but it's a mesoscopic system. When you start to do thermodynamics in this kind of small systems, with quantum mechanics playing a big role, interesting things may start to happen, because so we are pretty sure that when you have a small enough number of particles and you do thermodynamics, you should start to see fluctuations in the thermodynamics. The usual thermodynamics is derived under the assumption that the system is infinite in practice. Okay, so when you relax that assumption, strange things start to happen. So there are fluctuations in the usual, with respect to the usual laws of thermodynamics. So that could be something that could happen. But also, when you start to test the thermodynamics at this different length scale and this very low temperature with these strange laws governing the atoms, who knows what you can find out. So, I think that's the main point. We're interested in testing the laws of nature in a new setting and see if something interesting happens. I think that's the main point.
So that's then probably a pretty new kind of system which has not been explored so much yet.
Actually, it's not that new, because they started to do experiments on this kind of stuff in the 90s, so it's fairly understood. But as far as I know, trying to implement a thermal cycle in this kind of system is something that was not done before.
So just for me to understand it a little bit better, so the atoms have to be in a very small spot. How is that actually working? So how do you keep them in a spot? Are they charged? Are you using ions, or is it?
No, they are neutral. So you can keep them in place with some devices which are called magneto-optical traps. So in practice, you can confine them using a magnetic field.
You are basically starting off with a, let's say, kind of hot gas cloud, which is probably at room temperature when you let the gas flow inside, and then you have probably different kind of techniques which you use in order to cool down the system.
Yes. So unfortunately, I don't know really all the details, because I'm not an experimentalist. So definitely it's not by any means trivial problem, the one of cooling down this kind of system so low temperature. But there are some problems, like so the final stage is called evaporative cooling. So in which, in practice, they usually describe this kind of procedure as very similar to the process of cooling down your mug of coffee by blowing some air on top of it. So what happens is that the hotter atoms go away, and in this way you can lower the energy and therefore the effective temperature of your system. The problem is that in this way you lose part of these atoms, so at a certain point you have to stop. And that's another cool thing that could happen, is that if this kind of procedure works, so we can manage to cool down at least one part of the system to a temperature lower than the one that we started at the beginning, and we do so without losing atoms, well, that could be also an important thing, because you find a way to cool down even further a system which is already very, very, very cool. So
without any loss. Yeah, that's really amazing. I mean, in our lab we also do low temperature. We just call it low temperature, not ultra low temperature. But the lowest temperature that we are reaching are in the millikelvin regime. So that's still orders of magnitude higher. And that's already quite an effort to get a system cooled down to these temperatures. But I think with these ultra cold atom gases, that's even way more advanced than the stuff that we have to do in order to cool down our systems. So there's probably quite a lot of experimental effort behind this, but of course you are rather studying the theoretical side of that system also. So how does that work? I mean, when you want to simulate, let's say 10 to the power of 3 or 4 atoms, you probably don't do that on your laptop, right?
Depends. Sometimes I do.
Really? That's
because I mean, it really depends on what you want to see from your system. So what you want to test about your system. Depending on that, you can choose a model which is more complex or less complex, and therefore more computationally expensive or less. So the basic thing, the most basic thing that you can do to simulate the dynamic of this kind of system, which is what we're doing now, is using the Gross-Pitayevsky equation, which is the one that we were talking about before, that I was studying during my bachelor. And so this is an equation which describes this collection of atoms in practice as a quantum fluid. In the end, it's just an equation which looks like the one of hydrodynamics once you get rid of the dissipation part, which of course in this kind of quantum system doesn't happen because you have superfluidity. That's the most easy thing that you can do, but then you can go up in difficulty as much as you want, because I mean, instead the most complicated thing that you could do is simulating the full dynamics with each particle described with its own orbital, and there are methods to do also that, but it becomes a little bit challenging when you deal with 10 to the 4th particle. That's close to not being doable. So
it's probably not even with a supercomputer possible to do that, right?
Yeah, I would say so.
Difficult. I mean, in the other cases, you probably also make use of the fact that you have some symmetries in your system, like what you told before, that you have bosons, which can then also become a condensate and then probably behave like one big quantum system instead of
exactly, yes,
same
at
systems.
At 0 Kelvin actually it's true, but of course you're not at 0 Kelvin.
So how does that actually look in practice? Like what kind of software are you using when you simulate? Is it like do you have to use C or something that is very efficient on a numerical side, or are you rather on the Python side of the spectrum?
For the simulation that I did, I used a C++ library, which is called QEngine. So you have to deal with C++, which can be, time consuming on its own. It's not like Python, but it's faster. So there are, many implementation like of GP solvers and optimal control of GP that you can find on the internet, developed by many different groups. But if you want to have something that is efficient, you have to go on something like written in C, C++, something like that. There is some stuff written in MATLAB, which is very easy to read, easy to understand, easy to write and everything, but usually you cannot be as efficient as you could be in C or stuff like that. Python is somewhere in between, because in the end, if you use the correct libraries, like SciPy, NumPy and that kind of stuff, in the end the low-level computation are handled by efficient kernels, so the performance are not so different. And actually, maybe after all, maybe that could have been a wiser choice, because when you start to open up the code written by someone else and it's written in C, that's going to be painful.
Yeah, I remember.
Whereas maybe in Python it's a little bit more.
And probably MATLAB is also a bit of a problem when it comes to licenses, right? I mean, probably you have a license if you need one, but I mean, it's always a mess to get a license. And then
if you're a student, usually it's not a big problem. But later on, that could be the case, because that depends really on the institution where you're working at. So.
Yeah. At the moment where you try to get on a cluster because you have more difficult computation, then you probably need to get to some programming language like C, right? So you're also using cluster computers, or is everything that you do so far basically done with one station, a computing station?
At the moment, I didn't really run super intensive jobs. I ran a couple of them, but a workstation was enough to handle them. I mean, it was still a workstation with many cores, 32 cores or something like that, so you still have to parallelize it somehow. But at the moment, yes, I didn't really have the need to go on a cluster or something like that. But I mean, that could happen quite soon.
So did you also change the library now, or is it the one in C, which C++, which you're using right now?
Actually, the funny thing is that the simulation part of the project is, I wouldn't say finished, but we sort of converged on a solution, which is actually a theoretical one. I mean, it doesn't use numerical optimal control. It's obtained by an analytic technique, which is called the shortcuts to adiabaticity. We ran some tests to see if this kind of solution was robust enough, and it looks like it is. So now actually we're focusing on more practical aspects on how to implement that kind of stuff in a true experimental setup.
So that requires a lot of collaboration with the experimentalists and a lot of discussions on how to realize the steps and then moving on step by step. So how did you find that analytical solution? Is it done on a whiteboard like we did it when we studied physics at one point in time, or are you using things like Mathematica or other tools to basically optimize that?
I used the internet because I found it in a paper, in a very nice paper, and that did exactly what we wanted it to do. So that was enough.
Oh, perfect.
We were lucky.
So literature research is also something that one should be capable of. Then I have a little bit of a game, you know, every episode is kind of an experiment in itself. I call it 1 or 2. So the idea is I have 10 pairs of 2 different words, and you always have to choose the first or the second one. And it's only fun if you do it fast. So don't try to think too long about it. Go with it quickly.
Okay.
Let's start off. So the first one is theory or experiment.
Theory.
Simulation or symbolic.
Simulation.
Pasta or pizza?
Pizza, but that's hard.
Feynman or Einstein?
Feynman.
Fermion or boson?
Boson.
Pannetone or Pandoro?
Another very, very hard one. Pannetone.
Okay, graphene qubit or spin qubit?
Graphene qubit.
Spin qubit or Majorana qubit?
Majorana qubit.
Tesla or Gauss?
Tesla.
Tesla or Fiat?
Fiat, of course.
And because you said you like Pannetone so much...
Ooh, now I'm thrilled.
I brought a little one, the Pannetone.
Oh my god, thanks.
So
it's really nice of you.
if you want, we can have it right now. I also brought some plates.
Why not?
So,
of course.
Everyone who's listening has to deal with the fact now that we will eat something during the conversation.
Very nice.
So for everyone who is listening to that and doesn't know what a Pannetone is, you should go ahead and search for that on the internet. I heard when I was in Italy still that there's always a competition going on between Panettone and Pandoro. There's always the question which one is sold more for Christmas. And it's always very close to 50-50, right?
I don't really know. It's here at this time of the year. Me and my friends have some arguments about that, and they are pretty heated ones. So that means that there is some, some division. Yeah, that could be very close to 50-50. Ooh, thank you very much.
You're welcome. Unfortunately, I don't have the coffee which would fit to that now.
Yes.
Hopefully this pandemic situation is going to end very soon so that we can kind of move back to the original life of a scientist, let's say. So are there any interesting conferences very soon? Or is there probably a lot of conferences are also digital now? So
yeah, actually I attended a very interesting one, which was on non-equilibrium thermodynamics. It was quite interesting because the guy that invented that solution we were talking about was there, and he gave a talk. And so now he, as far as I understand, his name is Adolfo Del Campo. So now, as far as I understand, he's working on doing this kind of stuff, but in open quantum systems. I mean, bring it in the perspective of implementing that experimentally. Well, what we're trying to do right now is quite challenging, but that will be at another level. But I mean, that's interesting from a theoretical point of view.
Okay. Was there also some breakout session where you could have a conversation with him, or was it rather only the talk and then?
Actually, there was one, but I could not.
But maybe if he listens to the podcast, he can contact you in some way.
That would be nice.
By the way, are you interested in getting in contact with some people? So who would kind of be interesting maybe for collaboration or something like that? Is there anything that is maybe missing in your work or some contributions that you would be interested in?
At the moment, I'm working also with on a deep learning approach to work on these practical problems related to the experiments. So I mean, any input on that side will be very useful, you know. But I guess that I think there is so many people out there working on deep learning and this kind of stuff that I could easily be submerged.
Yeah. Do you already have some idea how this is going to be integrated?
So I started to dive into the topic a month or so ago, and so now we arrived to have a good candidate for the architecture of the thing that we need to do, which will be a convolutional one for the main part. But I don't really know much about machine learning in general, so I'm really entering that field right now. And I mean, it's really vast. It's interesting in some sense, in some other sense, it's more of a trial and error, but I mean, it's fun, it's interesting. I see why a lot of people get thrilled about that.
So if there's anyone listening who's totally submerged in the field of deep learning, he can probably get in contact with you. So how can one actually reach you?
Well, there is my email. So that will be m.calzavara at fz dash, I think it's Jülich.
Yeah.
.de.
And of course, we will also put that in the show notes later on.
Cool. And I fear that's pretty much it.
Okay. So people can contact you via email.
This Pannetone is pretty good, by the way.
Yeah, I think the bigger ones are usually even a bit better. I prefer them a little bit more, but I mean, this is at least good for a start, right? To get into Christmas mood a little bit.
Yeah. I mean, usually the big Pannetone are more moist.
Is there anything that you would like to talk about, tell about a little bit?
Just a quick impression of how you handle things here in Germany, because it's pretty different with respect to Italy. I mean, I'm also following a German course. It helps you a lot to learn every new little bit of German in your everyday life. Is very, very useful. But it looks to me, I mean, tell me if I'm wrong, but it looks to me like you German like to overcomplicate stuff.
In what
and
sense?
It can be seen from your language.
Yeah, that's probably true. I mean, I know that a lot of also native English speakers, they always say it's really annoying that we always put the verb at the very end. So you always have to listen until the very end of the sentence to know what the person actually wants to say. And yeah, of course, we also like to make sentences very long. And then also something that we like to do is we like to connect words to make them one word. So then it becomes really, really long. That's also quite messy. So with that impression of the German course, I think we will end this episode. And I would like to thank you for your time and for your impressions. And hopefully you get a lot of positive feedback also for the explanations. So from my point of view, it was quite clear. I understood and learned quite a lot. And hopefully the listeners also did so. Okay, so thank you.
Thank you very much for asking me to come. It was very nice. I had fun. So
this episode this time was recorded in the Central Library in the Research Center of Jülich. But of course, the MFOQ is also located in different locations, which is Cologne, Aachen, Bonn, and partially also in Düsseldorf, I think. So we will also have some episodes from these other facilities very soon.